Hello, my name is Shaunik Nag, and today I'll be presenting Lab 5, Faraday's Law. So in this lab, we are simulating Faraday's Law by dropping a magnet through a tube of aluminum foil, and then we are using GlowScript to model the experiment, calculating the change in flux, induced current, net force, and the time it takes for the magnet to fall through the tube. Faraday's law is the main physical principle used in this lab, and it says that the change in flux induces an EMF or drives a current, and there's an induced magnetic field that opposes the change in flux, and the equation is shown on the right. In this experiment, as the magnet falls, its magnetic field increases in magnitude as it falls through the tube. Therefore, the induced magnetic field opposes the magnet's motion, and the magnetic force opposes gravity, which causes the magnet to fall more slowly. A rough sketch of the experiment is shown in the picture on the right. I used the magnet, tube of aluminum foil, and meter stick, and I additionally used the Magnemeter app on my phone to tell which pole is north and south on the magnet. We cannot use a ferrous tube like steel because it will generate its own magnetic field. I've listed the tube dimensions, the properties of the bar magnet, and I timed how long it would take for the magnet to fall through the tube's length and repeated it 5 times. For the coding part of this lab in GlowScript, I first started by creating the tube of aluminum foil as well as the bar magnet, putting in the parameters as shown on the previous slide. Next, I needed to calculate the magnetic field of the bar magnet, and I used the equation shown on the right, and this was from the lecture video included in the lab instructions. Subsequently, I calculated the change in flux with respect to time, treating the tube as a series of rings stacked on top of each other, and the equation is shown below. The next step was to calculate the ring current using Ohm's law, I equals V over R, from the previous step. And then I calculated the magnetic field of each ring as we were treating the tube, and subsequent magnetic force on each ring. And I used the equation shown on the bottom left, which is also from the video. I then initialized the magnetic force as a vector in the y direction. The only force besides the magnetic force in this experiment acting on the bar magnet is force of gravity, which I calculated in step 7 and then calculated the net force on the magnet as it traveled through the tube. I then finally calculated the bar magnet's velocity and position as it changed over time. Here I've shown the simulation part that my code generated. On the left is the tube with the magnet as it falls through the tube, and the red and blue lines represent the poles of the magnet. On the right is the velocity versus time graph, and according to the simulation, my magnet took 1.6 seconds to fall through the tube. For the discussion questions, if the resistivity of the conductor was reduced as close to zero as possible, the ring current would increase according to Ohm's law, which would then cause the magnetic force acting on the bar magnet to increase. Therefore, the magnet would fall much slower. Also, if there were holes or slots cut into the tube, the holes or slots would decrease the amount of rings present in the tube, which would therefore decrease the current, decreasing the magnetic force, and therefore the magnetic force acting on the bar magnet would be less than it was before, so the magnet would fall more quickly. Here I've summarized the times that it took for my magnet to fall through the tube according to the simulation and my actual experiment. In conclusion, this lab shows us how Faraday's law can be modeled through a simple experiment. And just to summarize Faraday's law, the change in magnetic field through the tube induces an EMF, and the magnetic field opposes the change in flux. And this causes the magnet to fall slower due to resistive force. Thank you for watching.